All right, a little bit of statistics. So, simple things. I want to look at just like some major concepts for us. When we talk about descriptive statistics, there are two main measures that are included in descriptive statistics. The first ones are measures of central tendency. Really, these are looking to characterize a typical member of the group. So here's my little sample of participants. They're on a little board on a fulcrum. And in order to get the board to be level, we had to move the fulcrum over to the left. Okay, so that fulcrum is kind of representing the mean, right? It's positioned in such a place where we're able to balance the board, even though we've got a cluster of people who are right next to each other on the left side, and on the right side we have one fewer participant, and they're spread out in a different way, right? So we had to place the mean in a position where it'll balance those things out. So let's compare that to the median, which would be the middle point of just the number. You would line up the values of whatever these dots are representing, and the middle value is the median. So half of the scores are less than the median, and half of them are greater than the median. So notice that the median and the mean don't match on this sample, right? The measures of central tendency don't always match each other, and so that can kind of be a little bit of a hint that your sample isn't very well clustered around the mean, or that this isn't a normal distribution. But there are better measures, like concrete measures, that'll let you know how widely dispersed your population is or your sample is. Dispersion is a measure of how closely the scores are grouped around the measure of central tendency. So here's another little sample. And what we'll notice is that the mean, median, and the mode are all 6 in this sample. But notice how there's one response on each of these numbers, except for number 6 where there's 2. That's the mode. The mode is the most common answer, right? So number 6 has 2, so that's the mode. It's halfway between the two ends, so like half of the scores are lower than that, half of them are higher than that. So it's the median. And then if we were to add up all of these scores and divide it by the total number of scores, we would get the mean, which is 6. Okay, so that's good. But this is a widely dispersed sample compared to, let's say, this sample, right, where I've got our burgundy balls. We've got 1 that's a 4, 3 that are 5, 3 that are 6, 3 that are 7, and 1 that's an 8. Okay, so look how much more tightly dispersed, more closely dispersed sample. Measures of dispersion give us numbers that represent how widely dispersed the data is. And that's really useful information, because what if you're conducting some kind of survey and literally every single person has a different number than everybody else? That's really hard to interpret. Whereas if people cluster together, you start to get certain kinds of patterns that give you some insight into like what the average person might think, stuff like that. What we're really talking about there is the normal distribution, a bell curve. When we have enough data, just about every characteristic follows a normal distribution. Just about every characteristic does that. And when I say enough data, it's not probably as much as you think. It's about roughly 5 participants for every item on your scale will give you enough data to produce a normal distribution. So yeah, things are pretty normally distributed given enough members of the population. Okay, so what makes a normal distribution normal is that the mean, median, and mode are all exactly the same. You know that I'm pointing at the mode because this is the peak of the curve, so that's where the most responses are. And then the mean, I can also tell you that the median is right here because half of the scores are lower than this, because see how we're at the 50% level if we point at the 0 there in the middle. So 50% of the scores are lower than that, 50% are higher than that. You're just going to have to trust me that if we were to add up all the scores and divide by the total number of scores, the mean would be there too. This is mean, median, and mode are exactly in the same place on a normal distribution. What's interesting about a normal distribution is that 65% of participants will fall within 1 standard deviation away from the mean. So if you go down 1 standard deviation or you go up 1 standard deviation, We add those all together, and actually if you add these values that are here, you'll find that it's roughly 65%. I did a little rounding, but roughly 65% will fall here. 95% of people in a normal distribution will fall within 2 standard deviations away from the mean. So what that means is that when we are doing research, not everybody's going to get the same score. That's true. Not everybody's going to have the same attitude. Not everybody's going to benefit from the same kind of training. But if we can hit 95%, that's pretty impressive. That's leaving just a few people out in the extremes that either underperform or overperform, something like that, right? Like if you can get 95% of people to show better attitudes following this training, or if we can find that 95% of the time you will hire a better employee if you follow this selection protocol, something like that, that's pretty impressive. And so that's what we're striving for, is to have, establish which characteristics are normally distributed, and then figure out strategies that would allow us to get to, the vast majority. Actually, honestly, most employers would be happy if you got to the 65%, where you're able to cover 65% of their employees. So let's talk a little bit about some of the statistical analyses that we do really commonly in psychology in general, IO psychology in particular. Correlations. A lot of times we're interested in whether one variable goes with another variable. And one of the ways that we can assess whether that's happening is by computing a correlation coefficient. A correlation coefficient, which is represented by a little r, is the strength of it represents the strength of the relationship between two variables. So there are different ways that the correlation coefficient might appear. So here on the left, I've got, on all three of them, the y-axis is job performance. On the left, I've got surfing skill being correlated with performance on whatever job this is. And you'll notice that everybody's sort of just randomly distributed, kind of in a circle. The correlation coefficient is 0. There is no relationship between surfing skill and whatever this job is that we're assessing. Obviously, the job is not surf instructor. So that's a non-correlated. The one in the middle, we're doing a correlation between job performance and mechanical comprehension. Now, apparently these go together. Apparently this job entails some mechanical comprehension. And so we're seeing what's called a positive correlation. I put a nice little plus sign there for you, where it's also a strong correlation. It's one of those numbers that I told you we never see in real data, which is 0.7. And so you see the correlation coefficient of 0.7. Notice that it's no longer a circle, it's much more of a collapsed oblong, right? The data is not lined up on a single line. That would be a correlation coefficient of 1. But they are highly correlated. Like people who are higher on mechanical comprehension are also better at the job, and people who are lower on mechanical comprehension are not as good at the job. If you go to the one on the right, we've got alcohol consumption as our correlated variable, and we're seeing a negative correlation. So again, it's a 0.7 value. So the oblong looks very similar, but now it's tilted a different direction. And what we're seeing here is that people who consume the least alcohol seem to be performing the best on the job, and the people who consume the most alcohol are doing the worst on the job. This is what correlations can tell us, is that these two variables go together. It doesn't say why, it just says that they do. It allows us to establish which variables might be related to each other. Now, if we discover that a variable goes with another variable, like mechanical comprehension or alcohol consumption goes together with job performance, we might want to perform a regression analysis on that, which is going to allow us to predict one variable from the other. We can use the coefficient of determination, which is just basically taking that R value and squaring it. And that gives us insight into the percent of variance that's accounted for by the predictor. So here we have the mechanical comprehension overlapping with job performance. Our R had been 0.7, so I squared it, and that gave us a 0.49. So what that means is that about 49% of the variability between people on job performance would be accounted for by their mechanical comprehension score. So if we know their mechanical comprehension score, we'd be about 50-50 being able to predict their job performance. Notice how when you square a correlation coefficient, it suddenly becomes not that much percent that's being accounted for. Let's say that the correlation coefficient had been 0.4. That's a really high correlation coefficient for most psychological characteristics. So we'll say it's 0.4. 0.4 squared would be 0.16. That means that 16% of the variability in one variable is being accounted for by the other variable. That's not very much. So, even a 0.7 correlation coefficient comes out to be only half about of the individual differences on job performance being accounted for by mechanical comprehension. That leaves a lot of room for a lot of other things to be playing a role. Now, I gave you some different kinds of research designs and things that you can do to collect data. And here's a nice little hierarchy of scientific evidence. At the bottom, we have like case reports, which would be case studies in the terminology I used, opinion papers, letters. We're climbing up cross-sectional studies, case control studies, cohort studies, randomized controlled trials. Okay, that was that true experiment that I mentioned. At the very tippy top would be the meta-analysis and systematic reviews. That's the top of the peak of scientific evidence. So in a meta-analysis, it's a methodology that you can follow to conduct quantitative reviews of other studies. So just to give you a simplification of what's going on, you take a bunch of different studies that all meet some kind of criterion. They've all used a particular measure, or they've all used a particular sample type, type of employee or something like that. They've all met some kind of criterion. So you take all those studies together, you take all their data as if it was one big study. You put it all together into one big analysis, and that gives you much more robust results. You have a lot more confidence that this is the real pattern when you've taken all of these different studies and put them together and treated them as one. So you're going to combine the results of multiple studies, and you arrive at the best estimate of the true relationship as a result of that. So if you ever come across in your reading something that says that it's a meta-analysis, first off, I have to tell you at the beginning of it, it's kind of boring because it'll tell you all the inclusion criteria and all the things that cause them to leave a study out and like that. And that's kind of boring. So hop to the next part where it tells you what the basic patterns were. Meta-analyses are really like they're the gold standard of telling us what the big picture is on a particular topic. All right. Well, I covered a lot of things in chapter 1. Hopefully you feel a lot more confident that you know the things that I told you would find out about in this chapter. And hopefully you enjoyed this introduction to IO psychology. I believe if I know my text correctly, I think the next subject in chapter 2 is going to be job analysis, and as it should be. So I will see you in the next chapter.